Welcome to DTK channel, lecture 6 of atomic and nuclear physics. This lecture is about X-rays. X-rays are part of electromagnetic spectrum. X-rays are very important in the modern medical field. Coming to the physics of X-rays, X-rays are produced when a fast moving electron is suddenly stopped by a target. This is how X-rays are produced. We are going to discuss the production of X-rays and characterization of X-rays and types of X-rays in this lecture. I am going to present this lecture in the following way. Introduction about atomic spectra and X-rays, then about atomic spectra, production of X-rays, continuous X-ray spectra, characteristic X-ray spectra, and finally summary of the discussions we are going to have. The study of atomic spectra provides more knowledge about atoms. In atoms, when electrons jumps from one energy level to another energy level, it emits and absorbs radiation. This is the basis behind production of spectral lines and spectrum in atomic theory. So, in modern science, atomic spectra are used to identify elements of atoms in wide range of objects, from distant galaxies, stars. That means all objects in the universe contains some elements. Those elements are analyzed by the spectroscopic techniques, where this atomic spectra is the fundamental concept. Emission of radiation from energy levels when an atom jumps from one energy level to another energy level. The theoretical basis of atomic spectra is the transition of electrons between energy levels in atoms. Bohr atom model throws light in the transition of electrons from one energy level to another energy level. For example, if an electron in a hydrogen atom makes a transition from n is equal to 3 to n is equal to 2 shell, the atoms emit a photon with a wavelength. Like that, any transition if you take, there will be an emission when the transition is from higher energy level to lower energy level. If the transition is from lower energy level to higher energy level, absorption of energy is taking place. This is the fundamental physics behind the atomic spectra. And coming to the emission, if we heat a gas, it emits lights of various wavelengths. In electromagnetic spectrum, there are many types of radiations are there, starting from radio waves till gamma rays. For monoatomic gases formed of only one kind of atom, the emission spectra contains only one light or a light of particular wavelength. We can't see all wavelengths or different wavelengths in the emission process when we heats up a monoatomic gas. When electron jumps from lower energy level to higher energy level, it absorbs energy, and when it jumps from higher energy level to lower energy level, it emits energy. An atomic spectrum is broadly classified into two categories: absorption spectra and emission spectra. When electrons jumps from lower energy level to higher energy level, it absorbs radiation, which is called stimulated absorption. Like that, stimulated emission is there, spontaneous emission is there. Spontaneous emission means when an atom jumps from higher energy level to lower energy level without any external force, then that a kind of radiation will come out. That radiation is spontaneous emission process. Stimulated emission means if you substitute or give some energy to the atom or molecule present in the higher energy level to come down, that type of radiation is called stimulated emission. Like that, atomic spectrum throws a light for understanding the basis of X-rays. Coming to the emission spectrum is the spectrum resulting from the transfer of excited atoms from higher energy level to lower energy level. There are two types of emission spectrums are there: continuous emission spectrum and line emission spectrum. Continuous emission spectrum is a spectrum consisting of all wavelengths and frequencies in a continuous manner. You can't see any gap between two wavelengths. Continuity will be there in that spectrum. This is also called as a band spectrum. Band of colors will be there. Line spectrum, coming to the line spectrum, is a spectrum occurring at special frequencies and not continuously distributed. The line spectrum does not emit from the material until it is in form of separated atoms or in gaseous state under low pressure. So, line spectrum emits radiation when the atom or gases are in a single monoatomic state or in a separated way. This is how emission spectrum can be learnt. Coming to the absorption spectrum, when light passes through certain gas or some material, some wavelengths in the continuous spectrum are found missing. These wavelengths are the same as those which appear in the emission spectrum of the gas and are called line absorption spectrum. Line absorption spectrum is dark lines of some wavelengths in the continuous spectrum of white light, and these lines due to absorption of vapor of the element present in a particular region. Using this concept, elements present in celestial bodies are revealed or analyzed. A light coming from a distant star or galaxy is analyzed using a spectroscopic technique. Dark lines will be there in the continuous color background. These dark lines corresponds to various wavelengths. So, corresponding atom or element is there in the celestial bodies. This is how spectroscopic techniques are used to reveal the elements present in various celestial bodies. This proves that there are hydrogen and helium elements in the solar envelope, where the spectrum of the sun contains the absorption spectrum lines of helium and hydrogen, which are called Fraunhofer lines. Fraunhofer lines are a vital invention in the field of optics, spectroscopy, which is used by astronomers to reveal the elements present in sun. Fraunhofer lines are absorption spectrum of the elements in the sun. Basically, those elements are helium and hydrogen elements. Sun's energy is due to nuclear fusion reaction. When hydrogen joins together or fuse together to produce helium, then helium joins together and produces required element. We got energy in the sun. Those energies are radiated to earth to keep the earth warm and a living environment. So, absorption spectrum plays a vital role to understand the hydrogen and helium present in sun. In this picture, you can see a continuous band. Here you can't see any gap. That's why it is called as continuous absorption atomic spectrum. Then emission spectrum. Here you could see different color lines in a black background. So, a particular wavelength is emitted here, red light. Corresponding wavelength will be 6000 angstroms. Then a blue light, corresponding wavelength will be around 400 nanometer or 4000 angstroms. So, this is the line emission spectra. Coming to absorption, as I said, you can see dark lines in a color background or white background. So, here this dark line corresponds to absorption of 6000 angstrom wavelength. In spectroscopy, there are data to relate the 6000 angstrom absorption to a particular atom. Like that, here some 4500 angstroms absorption has taken place. Here 4000 angstrom absorption has taken place. Like that, absorption spectra shows dark line in a continuous color background. So these are the basics of atomic spectra to understand the X-rays. X-rays are types of electromagnetic radiation with wavelengths ranging from 10 power minus 8 meter to 10 power minus 12 meter, that is 0.1 nanometer to picometer, and corresponding frequencies are about 1016 Hz to 1020 Hz. So X-rays are wavelength whose wavelength will be in the range of 1 angstroms. So that X-rays are used to analyze crystalline materials, and X-rays has a peculiar property. It will not penetrate through human bones, it will pass through small tissues and skins, but it will not penetrate through human bones. So that X-rays are widely used to reveal the inner part of human body, various inner parts of human body. These X-rays were discovered in the year 1895 by Wilhelm Conrad Röntgen, a professor at Wurzburg University in Germany. Röntgen noticed crystals near a high voltage cathode ray tube exhibiting a fluorescent glow even when he shielded them with dark paper. Amazing phenomena observed by Röntgen. Then he was searching for answer for this phenomena. The answer for this one is some form of energy was being produced by the tube, cathode ray tube, that was penetrating the paper covering the crystal and causing the crystal to glow. Röntgen called these unknown radiations as X radiations, unknown energy as X radiations. This is how X-rays born in the year 1895. Later, many experiments were done by many scientists to understand the properties and characteristics of the X-rays. One of the experiments showed that this radiation could penetrate soft tissues but not bone, as I told earlier. It would produce shadow images on photographic plates. That means it will affect the photographic plate like other radiations present in the electromagnetic spectrum. For this discovery, Röntgen was awarded the very first Nobel Prize in Physics in the year 1901. This is the electromagnetic spectrum. In this electromagnetic spectrum, you can see different radiations starting from long radio waves, then amplitude modulation radio wave, short radio wave, frequency modulated radio wave, then microwave region, then infrared region, visible light region, ultraviolet region, after that X-rays, after that gamma rays. So X-rays exist in the electromagnetic spectrum in high frequency range. If you look at the frequency this side, it starts from 10 power 16 Hz and ends at 10 power 21 Hz. So the frequency range of X-rays is between 10 power 16 Hz to 10 power 21 Hz. So automatically energy of these radiations will be very high, because according to Planck's hypothesis, frequency of a radiation is directly proportional to energy of the radiation. E is equal to h nu. With that principle, these X-rays are high energy radiations. Then in X-rays, two types are there, broadly speaking: soft X-rays and hard X-rays. Hard X-rays will coincide in some region around the gamma rays, but the source of production distinguishes the hard X-rays and gamma rays. Hard X-rays are produced from the electronic transition. Gamma rays are produced from the nuclear radioactive decay. This is how source of the radiation differentiates the production hard X-rays and gamma rays. Characteristics and properties of X-rays. X-rays are electrically neutral. That means if you pass an X-ray through an electromagnetic field or separately by an electric field and separately by a magnetic field, these X-rays will not be deflected, so that X-rays are electrically neutral. Then X-rays travels in straight line with a velocity of light, which is equal to 3 into 10 power 8 meter per second. This property of straight line motion or rectilinear motion of X-rays are used to focus the X-rays in order to radiate the specific region of the body being studied. X-rays produce biological and chemical effects, which means they can affect an organism by producing ionization. We know ionization means removing an electron from an atom, so it will become a positive ion, and attaching an electron to an atom, it will become a negative ion. So in a region, if you convert all the atoms, neutral atoms, into ions, then the region is ionized. This ionization process can be made by passing X-rays into that region. So X-rays will produce ionization. X-rays span a section of the electromagnetic spectrum and possesses not only one frequency but a band of frequencies. These band of frequencies depends on the set of electrons that lead to the generation of the X radiation. X-rays are not visible to the human eye or to animals, so detection of X-rays is possible only by means of instruments and photographic methods. X-rays produce images on photographic film and fluorescence on certain type of crystals. These properties are used to capture the X-ray images. X-ray produce secondary radiation and scattered radiation, which means that a biological object receiving X-rays produces new rays with different characteristics. So X-rays can be scattered, can be used to produce secondary radiations. X-rays are roughly classified into soft X-rays and hard X-rays, as I said earlier, while explaining the electromagnetic spectrum part of X-rays. Soft X-rays have relatively short wavelengths of about 10 nanometers, and so they fall in the range of the electromagnetic spectrum between ultraviolet ray and gamma rays. Hard X-rays have wavelengths of about 100 picometers. These electromagnetic waves occupy the same region of the electromagnetic spectrum as gamma rays, as I explained earlier. The only difference between them is their source. X-rays are produced by accelerating electrons, whereas gamma rays are produced by atomic nuclei in one of the 4 nuclear reactions. This is how hard X-rays and gamma rays can be distinguished. Coming to the production of X-rays, this is the schematic diagram to explain the production of X-rays. You could see a lead casing as the outer part of the X-ray instrument. Then inside that lead casing, a glass envelope is there. This glass envelope is vacuumized, containing vacuum. Then inside that glass envelope, anode is fixed, then cathode is fixed. This cathode is used to emit electrons. Using thermionic emission concept, electrons can be ejected from this cathode. Then this is the focusing cap. This red color one is the focusing cap, and this one is the filament. Tungsten filament is used mostly. Then this is the window to receive the produced X-rays. This one is the window to receive the produced X-rays, and this is the target material which stops the fast moving electrons or accelerating electrons, so that X-rays are produced. So this is the experimental setup, schematic diagram of experimental setup of X-rays. A current is passed through the tungsten filament. This is the tungsten filament. Through that a current is passed, so that it heats up. As it heated up, the increased energy in the tungsten filament enables electrons to be released from the filament through thermionic emission. The electrons are attracted towards the negative charges will be attracted by the positive electrode. So, the electrons are attracted towards the positively charged anode and hits the tungsten target with the maximum energy determined by the tube potential. As the electron bombard the target, they interact via Bemström hull. This is a German term, Bemström hull, which means breaking of the reaction, breaking the chain, Bemström, and characteristic interactions which results in the conversion of energy into heat and X-ray photons. That energy is converted, 99% of the energy is converted into heat and only 1% of X-ray photon is produced when a fast moving electron bombards the target. X-ray photons are released in a beam with a range of energies, which is X-ray spectrum, out of the window of the tube and form the basis for X-ray image formation, which is used in many medical fields in our day-to-day life. Apart from medical fields, it is primarily used to characterize a sample to understand the structure of a newly synthesized material. In material science, the usage of X-rays is very vital. It is used to reveal the structure of a newly synthesized material, and based on the structure, that material can be applied in various fields. So, that is the two prominent usage of X-rays. Coming to the X-ray spectrum, two types of X-ray spectrums are there. Continuous X-ray spectrum. The high energy electrons in continuous X-ray spectrum, the high energy electrons get decelerated by Coulomb's interaction with the target atom. These decelerating electrons emit continuous X-rays, as I told, German term Bemström lung, which means breaking of the continuity. When an electron loses its entire energy in a single Coulomb's interaction, then X-rays of minimum wavelength are emitted. The cutoff wavelength of the continuous X-ray spectrum is related to the accelerating potential applied between the cathode and the anode, which is given by the relation 12,400 by V, which is lambda is equal to hc. H is Planck's constant, c is the velocity of light, then E is the charge of the electron, V is the potential difference applied between the cathode and anode inside the Coolidge tube, which is the instrument used to produce X-rays. Typically, accelerating voltage is a few thousand volts and cutoff wavelength is of the order of an angstroms. In X-rays, the cutoff wavelength decreases when the accelerating potential of Coolidge tube is increased. So, coming to the intensity of X-rays, it increases with an increase in accelerating potential, and this intensity of X-rays depends on other factors like target materials used, then filament used. All these factors decides the intensity of the produced X-rays. In this spectrum, this is the X-ray spectrum. In this spectrum, you can see two spikes. These two spikes are characteristic X-rays. Here you could see a continuous line. This is the continuous spectrum. So, this spectrum is a mixture of continuous X-ray spectrum and characteristic X-ray spectrum. Characteristic X-rays are emitted from heavy elements when their electrons makes transition between the lower atomic energy levels. The characteristic X-ray emission, which is shown as the two sharp peaks in this figure, here I told two sharp peaks, occur when vacancies are produced in the K shell of the atom and electrons drop down from the higher shell to fill the gap arised in the K shell. The X-rays produced by transition from n is equal to 2, that is L shell, to n is equal to 1 level are called K alpha X-rays, and those for n is equal to 3 to 1 transition are called K beta rays. Here in this diagram that K alpha, K beta rays are there, no? So, this K alpha ray is produced when a transition takes place from n is equal to 2 to n is equal to 1. Then K beta rays are produced when a transition from n is equal to 3 to n is equal to 1 takes place. This is how characteristic X-ray spectrum are produced. Then coming to other types of transition, when the transition takes place from other higher level to n is equal to 2 are designated as L rays. Then to n is equal to 3 to 2 is L alpha rays, and n is equal to 4 to n is equal to 2 is L beta rays. So, like that you could see other X-rays here in this figure. You can understand the characteristic X-ray spectra very clearly. When this is n is equal to 1, that is K shell, and n is equal to 2 L shell, n is equal to 3 principal quantum number, n means principal quantum number, M shell, n is equal to 4 N shell, n is equal to 5 then you got LM and O shell. So, here K alpha, K beta, K gamma, K delta lines, then L alpha, L beta, L gamma lines, then M alpha, M beta lines. In material science, mostly this K alpha, K beta lines are used. So, when a transition takes place from n is equal to 2 to n is equal to 1, K alpha lines, transition from n is equal to 3 to n is equal to 1, K beta lines. Like that other K lines are produced. These M alpha, M beta lines are produced when a transition from n is equal to 4 to n is equal to 3, M alpha lines takes place. Then a transition from n is equal to 5 to n is equal to 3, then M beta lines are produced. This is how characteristic X-ray spectrums are labeled and understood. The frequencies of the characteristic X-ray can be predicted from the Bohr model. Then Moseley measured the frequencies of the characteristic X-rays from a large fraction of the elements of the periodic table and produced a plot of them, which is now called Moseley plot. Here in this figure you can see the Moseley plot of characteristic X-ray spectrum. So, here in y-axis you could see different elements in the periodic table. Then this is the frequency. So, a linear fit is there between the frequency and the elements. So, Moseley stated a law connecting the element and the frequency produced. Element means target element. So, if this is used as a target element, this type of X-rays are produced. That is the study made by Moseley. When square root of the frequencies of the characteristic X-rays from the element is plotted against the atomic number, a straight line is obtained. So, Moseley showed that K alpha X-rays followed a straight line when the atomic number versus the square root of the frequency was plotted. So, Moseley's law states that the wavelength of any particular line decreases as the atomic number of the emitter is increased. Very important law in understanding the X-ray spectrum and X-rays. Coming to the summary of the discussions we had, first we started with atomic absorption spectroscopy, then atomic emission spectroscopy. These two spectroscopy concepts are theoretical basics obtained from Bohr atom model. Then when electron jumps from lower energy level to higher energy level, it absorbs radiation. When it jumps from higher energy level to lower energy level, it emits radiation. Two types of X-ray emission spectra are there, continuous spectra and line spectra. When white light passes through certain gases, some wavelengths in the continuous spectrum are found missing. These wavelengths are the same as those which appear in the emission spectrum of the gas and are called line absorption spectrum. Then we learnt about X-rays, production of X-rays, X-rays are electromagnetic radiations about 10 power minus 8 to 10 power minus 12 meter. Two types of X-ray spectrums are there: characteristic X-ray spectrum and continuous X-ray spectrum. To learn more about X-rays, you can surf these websites. Thank you.